Hello, this is Nodari Vakhania at the first international online conference on algorithms. My intention today is to talk about our ongoing research project on traveling salesmen's problems in collaboration with PhD students Victor Pacheco and Frank Hernandez. You can see here the title of the talk. And what was our intention for the traveling salesman's problems was the design of approximation algorithms with a good practical performance, which run fast, consume little computer memory, and we thought that this is possible because of the nature of the Euclidean version of the paper of the problem, which permits to use some simple geometric considerations during the construction of the solution, and somehow these properties, geometric properties, somehow guarantee that the solution that will be generated should not be bad, and also it can be obtained in a relatively short time. The basic traveling salesman's problem can be described in terms of n objects that are often called cities, clients, but we will use the term points because we are dealing with two-dimensional Euclidean space. And we define a feasible tour that starts from any of the given points, visits all the remaining points exactly once, and returns to the initial point. So this kind of tour is supposed to be accomplished by a salesman in practical terms. What is the input? Input is an n by n matrix that specifies the distance from city, point I to point J, or the cost of the travel. Here we denote a feasible tour by t, and its cost is represented here. And the objective is to find a feasible tour with the minimum cost. Here are some possible applications of the problem. And what about our approach? So the first step is to create a Girding polygon that somehow bounds the area that is interesting for us in two-dimensional Euclidean space. Another good characteristic of this Girding polygon is that it already defines an optimal tour for the set of points that it contains. In the solution method that we propose, we use two strategies that we call insertion and inflammation strategies. So insertion strategy is more or less traditional. We start with a feasible tour determined by the Girding polygon, and then iteratively we extend the current partial tour with one additional point that is somehow we using based on the geometric considerations. We consider that this is the best choice currently. So it is somehow the closest point, and it yields the minimum increase in the cost. And with the inflammation strategy, we iteratively construct inner convex hulls, which are used for the construction of our tours. So these are partial tours which are inflamed, which are extended iteration by iteration. Let us give this kind of a small example with 6 cities, and here it is not necessary to give explicitly the metrics because we can see the distances in two-dimensional Euclidean space directly. So how we construct the Girding polygon first? We determine 4 support auxiliary vertices that we call V1 through V4. In this example, there are only 3 such vertices. 3 is enough. And then we just join these 4 vertices, or 3 in this example. So we can see here that the initial tour T0 contains these 3 points which are on the Girding polygon, and the set of vertices which remain are covered are here, 1, 3, and 6. So what is a general description of the method? Okay, so we first, as we said, construct a partial tour defined by the Girding polygon. Then we extend this tour iteratively to our first complete feasible solution. And then at phase 3, we iteratively try to improve this solution. It's more or less clear standard approach. So in this example, in order to extend our partial tour, which is defined by this Girding polygon, we have 3 possibilities: vertex 1, 3, and 6. And we calculate the cost of the insertion for each of them. And then the minimum cost is given by 0.6. So we include it first. Then the next one here would be vertex 3. So we use triangle equality to determine the cost of the inclusion of the next point, yes. at each iteration. So this was the minimum was first reached for 6, vertex 6, then 3, and then the last vertex is included between point 6 and 4. Now we use the standard 2-opt local search heuristic to improve the tour that was constructed on the previous stage. What we do is we try to remove a point from its current position and move it to a new position, resulting in a new tour. And then we take an option that results the maximum reduction of the cost, and we halt when we see that the current cost cannot be further improved. Here we give the experimental results, and here basic achievements say. As to the quality of the solution that we obtain, it is about, in average, it gives the same approximation gap as the state-of-the-art algorithms. It's about 7%. And at the same time, we were able to improve the state-of-the-art solutions for several problem instances, benchmark instances. At the same time, the proposed algorithm that we have just described is extremely fast. I mean, it's 684 times with a rough average estimation faster than the earlier algorithms. Also, it consumes a little computer memory. Now we turn to the next method that we also use for the same problem, the generic TSP problem, traveling salesman problem, that we call the inflammation method. Here we rely on the concept of an inner convex hull. Yes, that consists of points. These are yet, I say intuitively, these are yet uncovered points, which define a convex polygon, and such that the points that we have not yet considered at a given stage, or at a given iteration, all are in the area, in the exterior area of this polygon. We calculate special kind of point that we call centroid, averaging the coordinates of all the points. That is also used in our construction. We give an example here. So here we can see our initial convex hull, polygon, that includes all these points. There is no uncovered point inside this area. How it works? So this method that we call inflammation method starts with a minimum convex hull that we have just seen in the previous slide, and that immediately defines our initial tour R0. So initial convex hull P0 and partial tour R0, which coincides with P0 here. And then we construct at any iteration which follows, we construct our next at iteration I, we construct our next inner convex hull, Pi. Yes, and then we somehow merge the tour defined by Pi with the tour that we have constructed at the previous iteration, that is Ri minus 1. So merging these two tours, we have a tour that covers all the points which are in Pi and E in Ri minus 1. Now, here is the brief description of this method. Yes, this is just what we have just said. Now, to build a convex hull at each iteration, we use a specially determined theta angle, which is here. So for this point, the theta angle is determined this way, you're using the x-axis. So in technical terms, it can be expressed this way. So then, based on these theta angles, we construct the convex hull iteratively also, and on this stage of construction, which is just a fragment of a given iteration. So we have here 3 points, and we can see that if we add this point, then we get an angle which is theta angle, which is more than 180 degrees. So the corresponding curve will not be convex. Yes. Then we eliminate one of these three. This is the current vertex that we are considering, and these are neighbors of these two vertex, and the neighbors are determined by first ordering all the vertices according to non-increasing order of their theta angles. So this vertex is eliminated, and we consider the next vertex, which is here. Among these two vertices, we'll eliminate one which is further away from the centroid. So this is centroid, right? So once we discarded this vertex from the consideration while constructing our convex hull at iteration I, the next vertex in the sorted list according to the theta angles is this vertex. And so we repeatedly check the same condition, and in this case the angle is not more than 180 degrees, and so these three vertices remain in the polygon Pi that is constructed at iteration I. So this is a formal description of this procedure. And now, as we said, we join tour R at iteration I, we join tour R of the previous iteration with the convex, with the polygon defined by the convex hull of the current iteration P. of the P, I, which current iteration I. So what we do here is here we have any point on polygon P, which is Pi, that we have constructed at iteration I, and we want to join or include this point P in the tour that we have constructed at the previous iteration, which is here R as a parameter of this procedure. In fact, this is Ri minus 1. We consider all pairs of adjacent points in tour R and we determine the cost of the inclusion of point P between points X and Y, and we select the position or the pair X, Y, which results in the minimum cost, yes, and so on until all points of polygon P are included. In tour Ri minus 1, that results, now we have a new tour of iteration I. That includes all these points which are on P and which belong to R. Here is an example illustrating this procedure. Here are some results. Now we turn to the bounded multiprocessor version of TSP. So in this version we have, besides the data, basic data from TSP, we have especially selected or given point, which is called a depot. And now we construct, the aim is to construct n feasible tours. So each tour starts and ends at the depot. Here is the depot. With the bounded version of this problem, there is a limit lower and upper on the amount of points in each tour. So the lower bound is M min, upper bound is M max. Yes. And these K feasible tours define a complete solution for the BMTSP problem, bounded multiprocessor TSP problem. And on this example, we have 3 tours constructed. This is the depot, different colors, and union of these 3 tours define a feasible solution, given that MM is no less than 3 and max here can say 4 or 5. So now we represent each feasible tour this way. It starts in depot, ends in depot, and this is a feasible solution that contains all these K tours. The cost is defined similarly as for the TSP problem, and the total cost for the solution T is sum of these costs. Yes, and so the objective is to find feasible tour that minimizes the total cost, which is sum. So in this problem, we have to minimize the sum of the costs. And here, this PCI algorithm that we call for bounded MTSP problem, it somehow extends the TSP algorithm, that the insertion method that we have just described, the first one. So yeah, the difference is that at phase one, we have to partition the whole set of points. Then at phase two, we construct feasible solution, and again at phase three, we improve it. How we carry out the partition, we determine k additional points. Here are these extreme auxiliary points. These are determined based on the distance from the D port, and then we construct initial tours which contain the minimum required number of points. Each of these tours contain minimum required number of points. And then we try to extend. So if this solution contains all the points, then it is also feasible. Otherwise, it is not feasible because there are some uncovered points, which are here, these ones. And then what we do is at the next stage, based on some, again, simple geometric considerations, we extend some of these k tours so that the restriction on the maximum number of points in each tour is respected, and all the points are covered, so they are included in one of the constructed tours. So this is our first feasible solution. And then we use, once we have this, so in fact, this is not a feasible solution, but a feasible partition, sorry. And now once we constructed this feasible partition, we construct, for each of these partitions, we construct a feasible tour using our earlier described method, insertion method for TSP, and this already results in a first feasible solution. Yes, and then at phase two, similarly as in the case of our first method for TSP, we carry out some kind of an improvement. We select a vertex from one of the tours and try to move that vertex to another tour so that the total cost is reduced as much as possible. So we do not go now into the details of such kind of a procedure. We give some experimental results, and what is again a summary of the experimental results is that again, as for the TSP problem, the approximation gap is not larger than 7%, and for several instances, again, we were able to improve state-of-the-art solutions. So far we have tested just 16 benchmark instances, but we plan to create more benchmark instances by transforming known TSP or MTSP instances to the instances for the bounded version of the problem. And again, this method is much faster than known ones. So average rough estimation is 132 times faster. So what we can say finally, on one hand, as we could see, our method relies on simple, non-extraordinary findings. On the other hand, by combining these simple geometric heuristic considerations, surprisingly, we were able to obtain solutions of a good quality, which are competitive and comparable with the state-of-the-art solutions. And again, so as we have already mentioned, our method, our methods create solutions very fast, much more faster than state-of-the-art algorithms, which are basically genetic algorithms. Our algorithm obviously is not a genetic algorithm, it's just a direct combinatorial heuristic method. And also, as already mentioned, it consumes a little computer memory. So thank you for your attention. Enjoy the next talks on the first online conference on algorithms. Thank you very much for your attention. Goodbye.